Look up at the night sky, and you'll see a canvas of stars, familiar constellations, distant planets, the shimmering arc of our Milky Way. But just beyond what the naked eye can easily spot lies something extraordinary, a place where the rules of the universe seem to bend and twist in ways scientists are still struggling to explain. Welcome to the Large Magellanic Cloud, our cosmic neighbor and a dwarf galaxy packed with mysteries that defy imagination. This isn't just another patch of space. It's a laboratory of the bizarre, a realm where stars behave strangely, gas clouds glow with unexplained energy, and entire systems seem to operate by their own hidden logic. And today, we're diving deep into 30 of its most jaw-dropping phenomena, each one more puzzling and visually stunning than the last. What makes the Large Magellanic Cloud so special? For starters, it's close enough to study in stunning detail, yet distant enough to keep its secrets guarded. Unlike the orderly spiral of our Milky Way, this galaxy is a chaotic, star-forming powerhouse, where supernovas erupt with startling frequency and massive stellar nurseries churn out stars at a rate that should be impossible. Some of its regions glow with a light that shouldn't exist, while others vanish into darkness without a trace. It's as if the laws of physics themselves are being rewritten here, and astronomers are scrambling to decode what's really going on. This isn't just about distant lights in the sky, it's about the very fabric of reality. The Large Magellanic Cloud challenges everything we think we know about how galaxies form, how stars live and die, and even how dark matter might be shaping the universe in ways we never anticipated. From its eerily empty voids to its hyperactive star clusters, each mystery we explore today will pull you deeper into the enigma. So buckle up, because we're about to embark on a journey through one of the most fascinating corners of the cosmos, where every discovery raises new questions, and the answers might just rewrite the textbooks. Ready to see what's hiding in the shadows of the Large Magellanic Cloud? Let's begin. The Tarantula Nebula is the crown jewel of the Large Magellanic Cloud, a raging cosmic furnace where stars are born at a pace that puts our entire Milky Way to shame. But what really steals the show here isn't just the stellar fireworks, it's the enormous, delicate structures known as superbubbles. Imagine a balloon the size of hundreds of solar systems, blown outward by the relentless winds of newborn stars and the shockwaves of their explosive death. That's exactly what's happening in the heart of this nebula, where these colossal bubbles stretch across hundreds of light years, sculpting the galaxy itself. Hubble's sharp eye has captured these formations in breathtaking detail, revealing intricate webs of gas and dust torn apart by the sheer energy pouring out from the stars within. Each bubble starts when a cluster of massive stars, some weighing in at over 100 times the mass of our Sun, blasts out torrents of charged particles at nearly 1,000,000 miles per hour. Over time, these stellar winds carve out vast cavities in the surrounding gas, and when the biggest stars reach the end of their lives, they don't fade quietly, they detonate as supernova, sending shockwaves that expand these bubbles even further, like cosmic echoes rippling through space. But these aren't just pretty cosmic decorations, they're galactic architects. As superbubbles grow, they push material outward, triggering new waves of star formation in their wake, while also funneling heavy elements forged in stellar explosions into the wider galaxy. Without them, the Large Magellanic Cloud might look completely different, far less dynamic, far less vibrant. They're proof that destruction and creation are two sides of the same coin in the universe, and nowhere is that more obvious than in the swirling chaos of the Tarantula Nebula. Drifting through the emptiness between the Large Magellanic Cloud's bustling star clusters, there's a cosmic anomaly that shouldn't exist, the LMC N55 Nebula, a ghostly island of glowing gas floating in near-total isolation. While most nebulae are tangled within dense stellar neighborhoods, this one sits eerily alone, like a single lantern in a vast, dark sea. Its delicate blue tendrils ripple across hundreds of light years, lit from within by a handful of young, searingly hot stars. But don't let its dreamy appearance fool you. Those same stars are tearing their cradle apart with torrents of ultraviolet radiation, sculpting the nebula's fragile beauty through sheer violence. What makes LMC N55 so baffling isn't just its isolation, it's the fact that it's thriving in what should be a sterile wasteland. Normally, gas clouds this far from galactic hubs dissipate quickly, shredded by intergalactic winds or simply too sparse to birth stars. Yet here, against all odds, stars ignited, their fierce light punching through the nebula's veil to create one of the most hauntingly luminous structures in the galaxy. Telescopes reveal intricate pillars and cavities etched by stellar winds, a snapshot of creation and destruction playing out in slow motion, the real mystery. How this delicate ecosystem even formed? One theory suggests it's the remnant of an ancient, collapsed supershell, a galactic fossil from a time when titanic supernova carved voids in the LMC's gas. Another proposes that rogue gas streams pulled from deeper in the galaxy somehow coalesced here in perfect balance. Whatever the answer, LMC N55 stands as a reminder that the universe loves breaking its own rules, and that even in the quietest corners of space there's chaos dressed in elegance. Among the countless stars in the Large Magellanic Cloud, one stands out not for its brightness but for its sheer audacity. HV 2112 isn't just moving, it's fleeing. This supermassive star rockets through space at speeds that defy logic, leaving astronomers scrambling to piece together its violent past. Most stars orbit the galaxy's center in predictable paths, but HV 2112 behaves like a cosmic outlaw hurtling through the void fast enough to escape the galaxy's gravitational grip entirely. So what sent this behemoth on its one-way journey into the unknown? The leading theory is as dramatic as the star itself. Picture a binary system, two massive stars locked in a deadly dance. When one of them exhausts its fuel, it doesn't just fade away. It detonates in a cataclysmic supernova, releasing enough energy to fling its surviving companion into the abyss like a slingshot. That's likely HV 2112's origin story. A stellar partner's violent death propelled it to unimaginable speeds, transforming it into what scientists call a hypervelocity runaway. But here's where the mystery deepens. This star isn't just fast, it's chemically bizarre. Spectroscopic analysis reveals an atmosphere choked with heavy elements like zirconium and yttrium, materials typically forged in supernova furnaces or the hearts of neutron stars. Yet HV 2112 shows no signs of being a neutron star itself. Some researchers speculate it might have once orbited a Thorn-Zitkow object, an exotic hybrid star with a neutron core hidden inside a gaseous envelope, though such objects have never been definitively observed. Others suggest it siphoned material from a companion before the explosion, enriching itself with rare elements in the process. Whatever the truth, HV 2112 composition is a fingerprint of chaos, a relic of interactions too extreme for our current models to fully explain. What's clear is that this star refuses to follow the rules. Its speed, its chemistry, even its very existence challenge our understanding of stellar life cycles. And as it streaks toward intergalactic space, it leaves behind more than just a trail of light. It's a reminder that the universe still holds secrets too strange for textbooks. Just a short hop across the Large Magellanic Cloud from each other, two supernova remnants tell wildly different stories of stellar death. N49 and N63A might appear as mere smudges in early telescope images, but zoom in, especially with Chandra's X-ray vision. And these cosmic crime scenes reveal intricate details that leave astronomers questioning everything. Take N49 first, a tangled wreckage of stellar material, but with a bizarre twist, a colossal magnetic filament scientists call a cosmic rope. This snaking structure, stretching over 30 light-years, crackles with energy, glowing fiercely in X-rays as if something invisible is still powering it decades after the explosion. What could create such a spectacle? Imagine a massive star's final moments, its core collapsing into an ultra-dense neutron star, but not quietly. As it implodes, magnetic fields get amplified to incomprehensible strengths, billions of times stronger than Earth. Those fields don't just vanish, they snap like rubber bands, recoiling outward and twisting the surrounding debris into this glowing magnetic scar. Some researchers speculate the neutron star at N49's heart might be a magnetar, a rare breed spinning so fast it generates continuous flares. If true, it's a celestial lighthouse beaming energy into the rope like an eternal power source. Now shift your gaze to N63A. At first glance, it's another debris field, but look closer. Shockwaves from the explosion haven't just expanded, they've slammed into dense gas clouds lurking nearby. The collision is pure cosmic violence. Chandra's images show these waves plowing through the gas like tsunamis, heating it to millions of degrees and sculpting eerie, bubble-like formations. The aftermath, a laboratory for how supernovas seed galaxies with heavy elements. As those shockwaves churn, they're injecting oxygen, silicon, and iron forged in the star's death throws into the surrounding material, enriching future generations of stars and planets. What's fascinating is how differently these remnants behave despite their proximity. N49's magnetic drama suggests a star with extreme internal dynamics, while N63A's shockwaves expose the messy interplay between stellar explosions and their environments. Together, they're a masterclass in destruction, one leaving behind an electrified monument, the other a chemical footprint that will linger for millennia. And in their chaos, they hint at a deeper truth. No two supernovae are ever alike, stretching across nearly a third of the Large Magellanic Cloud like a shadowy serpent. The so-called Dark River isn't just another dust cloud, it's a cosmic enigma on an unimaginable scale. This colossal dust filament spans 30,000 light-years, weaving through the galaxy's outskirts and swallowing starlight whole. To the naked eye, it might look like emptiness, a void where the galaxy simply stops, but the truth is far more fascinating. This river of darkness is actually a roadmap, a clue to the hidden architecture of the LMC, revealing secrets about where stars are born and how matter moves in the shadows. What makes the Dark River so remarkable isn't just its size, it's what lies beneath the surface. Unlike typical dust lanes that simply block light, this filament acts like a cosmic sponge, soaking up radiation and re-emitting it in infrared wavelengths. Telescopes like Spitzer have peered into its depths, uncovering a labyrinth of colder, denser material that doesn't just obscure stars, it fuels them. These dust particles are the raw ingredients for future stellar nurseries, waiting for the right gravitational nudge to collapse into new suns. The filament's meandering path traces the invisible scaffolding of the galaxy's magnetic fields and gas flows, showing us where the next generation of stars might ignite. Here's the twist: the Dark River shouldn't be this stable. At its length, tidal forces from the LMC's interactions with the Milky Way should have shredded it eons ago. Yet it persists, a defiant ribbon of darkness resisting the chaos around it. Some scientists argue it's held together by dark matter, an invisible gravitational glue keeping the filament intact. Others suggest it's a fossil structure, a relic from when the LMC first formed. Its dust slowly settling into this eerie, elongated shape over billions of years. But the most tantalizing possibility, the Dark River might be a cosmic conveyor belt. Its dust isn't just sitting idle. Observations suggest it's slowly drifting toward the galaxy's heart, carrying the raw materials for star formation into bustling regions like the Tarantula Nebula. In this way, the filament isn't just hiding light, it's quietly shaping the future of the entire galaxy, one dust grain at a time. So while it might look like a mere shadow, the Dark River is anything but empty. It's a dynamic, living structure, proof that even in the darkest corners of the universe, there's motion, purpose, and the promise of creation. Tucked away in the Large Magellanic Cloud, there's a cosmic powerhouse that defies classification, LMCX3, a black hole locked in a deadly dance with a companion star. But this isn't just any black hole system. It's a microquasar, a scaled-down version of the universe's most energetic phenomena. Imagine a quasar, those brilliant, galaxy-spanning behemoths fueled by supermassive black holes, but crammed into a system small enough to fit within a single star cluster. That's LMCX3, and its behavior is anything but predictable. What sets this system apart are its violent, erratic X-ray flares. Most black hole binaries pulse with a steady rhythm as they siphon gas from their stellar partners, but LMCX3 erupts without warning, its brightness spiking by factors of hundreds in mere hours. These aren't gentle flickers, they're full-blown tantrums, as if something deep within the system's heart is tearing itself apart. The culprit, a wildly unstable accretion disk, the swirling maelstrom of superheated gas spiraling into the black hole. Picture a whirlpool where the water suddenly boils over, ejecting massive jets of material at nearly light speed. That's what happens here. Normally, accretion disks behave like orderly drains, but LMCX3's disk fragments under extreme magnetic forces, creating pockets of gas that collapse chaotically into the black hole in sudden, violent bursts. Each collapse unleashes a torrent of X-rays, lighting up telescopes like a cosmic strobe. The real mystery isn't just the flares, it's how this microquasar mimics its gigantic cousins. Full-scale quasars shine by swallowing entire stars and gas clouds, yet LMCX3 achieves similar brilliance with nothing more than a trickle of stolen stellar wind. Some theorists argue its black hole must be spinning at near breakneck speeds, amplifying its appetite through sheer rotational energy. Others point to its unique magnetic field geometry, which might funnel material into tighter, hotter streams than usual. But here's the twist. Unlike true quasars, LMCX3's outbursts don't last. They flare up, dazzle observers, then vanish just as quickly, leaving astronomers scrambling to explain where the energy goes. Some suspect hidden jets punching through the surrounding gas too faintly to detect. Others propose the black hole burps, ejecting excess material in dark, cold clouds. Whatever the answer, one thing's clear: this tiny titan is rewriting the rules on how black holes feed, proving that even in miniature, the universe's most extreme physics can't be tamed. Hidden within the swirling arms of the Large Magellanic Cloud, there's a stellar nursery that looks like it's been plucked straight out of a sci-fi spectacle, the so-called blue blob. This tightly packed cluster of young stars burns with an intense blue hue, their light so concentrated it almost looks like a single glowing jewel against the dark backdrop of space. But what's truly baffling isn't their brilliance, it's what's missing. Unlike most newborn stars, which nestle snugly within the gas clouds that birthed them, this group sits in eerie isolation, as if the cosmic womb that created them vanished without a trace. How does a cluster of stars this young, some barely a few million years old, end up floating in near-empty space? Typically, stellar nurseries cling to their gas clouds for tens of millions of years, gradually dispersing them through stellar winds or supernova shocks. But the blue blob defies that logic. Its stars are practically naked, with hardly a wisp of gas left around them. One theory suggests an extreme burst of star formation occurred here, so intense that the radiation pressure from all the newborn stars blew away their birthplace in record time. Picture a room full of people turning on blinding flashlights all at once. The sheer force of light alone could clear the space. Another possibility is even more dramatic. This region might have been hit by a shockwave from a nearby supernova, a cosmic bulldozer sweeping away the gas before these stars had a chance to fully form. Observations reveal faint traces of expanding shells around the cluster, lending weight to this explosive idea. But there's a twist. The stars here aren't just young, they're also unusually massive. Most star-forming regions produce a mix of sizes, but the blue blob seems to have skipped the small stars entirely, birthing only giants. That skews the math, making it even harder to explain how their surroundings disappeared so quickly. What's clear is that this cluster rewrites the rules of star formation. It's a cosmic paradox, a group of infants that somehow outran their cradle, leaving astronomers to piece together how such a thing could even happen. And as telescopes probe deeper, one question lingers. Is the blue blob a rare fluke or a sign that our understanding of stellar birth is missing a crucial chapter? Deep in the heart of the Large Magellanic Cloud, two cosmic specters tell very different stories of destruction and rebirth. DML 316, nicknamed the Colliding Ghosts, is an eerie sight, two glowing supernova remnants that appear to overlap in space like celestial phantoms. But looks can be deceiving. While these wreckage clouds seem locked in an eternal embrace, they're actually separated by hundreds of light years, drifting past one another in a cosmic coincidence frozen in time. The real magic happens when you observe them through different wavelengths. In visible light, they're ghostly shells of gas but switch to X-rays, and Chandra reveals their violent hearts, superheated materials still expanding from explosions that occurred millennia apart. What makes DML 316 so fascinating isn't just the illusion of collision, it's the stark differences between these remnants. The larger shell glows faintly, its shock waves slowed by plowing into denser gas, while the smaller one burns fiercely in X-rays, hinting at a more recent energetic explosion. Together, they're a time lapse of stellar death, showing how supernovae interact with their surroundings across generations. Yet despite their dramatic appearance, these ghosts are surprisingly quiet. Unlike typical supernova remnants that light up their neighborhoods, these two drift almost silently, their energy dissipating into the void with barely a ripple. Now shift your gaze to DML 50, the superbubble, and the contrast couldn't be sharper. Where the colliding ghosts are subtle and eerie, DML 50 is a gaping hole in space, a colossal cavity over 500 light-years wide, blasted out by the combined fury of stellar winds and supernova. Imagine a soap bubble the size of a solar system, except this one is filled with chaotic energy. Inside its thin shell, dozens of massive stars unleash hurricane-force winds, sculpting the gas into delicate filaments visible in ultraviolet. But the real spectacle happens when you combine X-ray and radio observations. The cavity's interior glows faintly with million-degree gas, while its edges shimmer with compressed molecular clouds, the birthplaces of future stars. Here's the twist: DML 50 shouldn't exist in its current form. Mathematical models predict such bubbles should collapse under their own turbulence long before reaching this size. Yet it persists, defying expectations. Some researchers think dark matter might be lending invisible support, its gravity subtly reinforcing the structure. Others argue that sequential supernova exploding in just the right rhythm have pumped energy into the bubble like a cosmic bellows, keeping it inflated against all odds. Together, these two phenomena showcase the dual nature of chaos in the cosmos. DML 316 is a quiet, almost poetic dance of remnants, while DML 50 roars with the unbridled energy of creation and destruction intertwined. One is a fading echo, the other a living engine, and in their differences they reveal a universal truth, that even in death, stars shape the galaxy in ways we're only beginning to understand. At the core of the Tarantula Nebula lies a stellar gladiator arena. The R136 cluster, a seething cauldron of young, monstrous stars packed so tightly they blur together in a blaze of blue-white fury. This isn't just any star cluster, it's a cosmic heavyweight champion, home to R136A1, the most massive star ever discovered. Tipping the scales at over 250 times the mass of our Sun, This behemoth burns with the brightness of nearly 9 million suns combined. But its sheer size isn't the only jaw-dropping feature, it's the sheer violence of its existence. R136A1 and its siblings are stellar titans living on borrowed time. Their enormous mass means they burn through their nuclear fuel at a breakneck pace, shining millions of times brighter than our sun, but destined to explode in spectacular supernova within a few million years, a cosmic blink of an eye. Their ultraviolet radiation is so intense it ionizes the surrounding gas, stripping electrons from atoms and creating a glowing cocoon around the cluster that's visible across interstellar distances. Telescopes like Hubble capture this maelstrom in stunning detail, revealing a landscape where stellar winds collide like hurricane-force gales, carving out vast cavities in the nebula. What makes R136 truly bizarre isn't just the individual stars, it's how they interact. In such a crowded environment, stellar collisions aren't just possible, they're inevitable. Imagine two massive stars grazing each other, their outer layers torn away in violent tidal interactions, or even merging entirely to form an even larger, unstable monster. Some theorists suggest R136A1 itself might be the product of such a merger, explaining why it defies current models of how large stars can form naturally. And then there's the cluster's future, a fireworks display unlike anything in our galactic neighborhood. When these stars finally go supernova, their explosions won't just be isolated events. They'll trigger chain reactions, their shockwaves compressing nearby gas and potentially igniting new rounds of star formation, even as they obliterate their surroundings. Some may collapse into black holes so massive they dwarf typical stellar remnants, leaving behind gravitational footprints that could warp the cluster's dynamics for eons. R136 is more than a collection of stars. It's a ticking time bomb, a laboratory for extreme physics, and a preview of the chaos that shaped the early universe. And as we watch it blaze defiantly against the dark, one question lingers. What new rules of stellar life and death will we learn when this cosmic powder keg finally ignites? In the outer reaches of the Large Magellanic Cloud, a star named HV11423 staged one of the most baffling cosmic performances ever recorded, a flare-up so intense it outshone its normal brightness by a factor of 1,000. For weeks, this aging red supergiant burned like a beacon, rivaling the luminosity of entire star clusters before fading back into obscurity. But here's the twist: it didn't explode. Unlike a supernova, which marks a star's catastrophic demise, HV11423 survived its own outburst, leaving astronomers to grapple with a critical question: what just happened? One camp argues this was a supernova imposter event, a near-death experience where a star teeters on the edge of destruction but pulls back at the last moment. Picture a massive balloon inflating to its limit, the surface thinning and trembling, yet somehow not popping. In stellar terms, HV11423's core may have become so unstable that it triggered violent pulsations, ejecting colossal amounts of material into space without fully rupturing. Telescopes detected vast shells of gas expanding outward at hundreds of miles per second, enough to blanket entire solar systems. These ejecta, rich in carbon and oxygen, suggest the star was purging layers forged in its nuclear furnace, like a cosmic exhale after holding its breath for millennia. But another theory paints an even wilder picture. Some researchers propose this outburst wasn't a death rattle, it was a rebirth. Red supergiants are notoriously messy eaters, often accumulating thick shrouds of dust that choke their own light. What if HV11423's sudden brilliance came from clearing this cosmic clutter? Imagine a clogged drain suddenly bursting open. The built-up pressure releases in a torrent, and for a brief moment, everything flows freely. In stellar terms, magnetic flares or internal upheavals might have blasted away obscuring material, revealing the star's true brightness before new dust could form. The most compelling clue, HV 11423's temperature didn't spike like a true supernova. Instead, it hovered in the cooler range typical of red supergiants, just vastly more luminous. This hints at a radical expansion of its surface area, as if the star swelled to an even more monstrous size before settling back down. Such behavior blurs the line between eruption and evolution, challenging our definitions of stellar life cycles. Whether a near catastrophe or a transformative episode, HV 11423's outburst forces us to rethink how stars behave in their final chapters. It's a reminder that even the most well-studied giants can still surprise us, and that the universe has a flair for drama when we least expect it. From a distance, the Large Magellanic Cloud appears to twist gracefully through space, its stars arranged in what looks like a single, sweeping spiral arm curving away from the galaxy's core. But here's the cosmic prank: that elegant structure isn't real. Unlike classic spiral galaxies where arms form naturally from density waves, the LMC's iconic curve is an elaborate illusion, a celestial mirage crafted by the relentless gravitational tug of war with our Milky Way. The culprit, tidal forces. Imagine holding a loaf of bread by one end while a friend pulls from the other. The middle stretches and crumbs scatter in a curved trail. That's essentially what's happening to the LMC on a galactic scale. As it orbits the Milky Way, our galaxy's gravity grabs the near side more fiercely than the far side, distorting the entire dwarf galaxy like putty. Stars and gas on the outskirts get stretched into this deceptive arc, creating the impression of a spiral arm where none truly exists. Computer simulations reveal the process in stunning detail, showing how over millions of years this gravitational ballet reshapes the LMC's structure without any of the internal mechanisms that normally produce spirals. What makes this illusion so fascinating isn't just the physics behind it, it's the implications for how we classify galaxies. The LMC has long been labeled an irregular galaxy, a chaotic jumble without clear symmetry. But the false arm blurs that definition, proving that even a galaxy's basic shape can be borrowed, a temporary facade imposed by its neighbors. Telescopes have caught the distortion in action, with the galaxy's outer regions visibly lagging behind its core, like a cosmic tail dragged through intergalactic space. And the story gets stranger. Recent studies suggest the Milky Way isn't the only actor here. The small Magellanic Cloud, the LMC's smaller companion, adds its own gravitational twists, yanking on the system in ways that amplify the asymmetry. This three-way dance creates kinks and wrinkles in the false arm, giving it a frayed, almost braided appearance in radio observations. There's even evidence that the LMC might be losing entire star clusters to these tidal forces, scattering them along its orbital path like celestial breadcrumbs. But the grandest revelation, this tidal tail isn't static. As the LMC continues its slow death spiral toward the Milky Way, simulations predict the false arm will grow longer and more pronounced, eventually shredding entirely, leaving behind a stream of stars as a relic of this gravitational sleight of hand. It's a reminder that in the cosmos, nothing is ever quite what it seems, and even a galaxy's silhouette can be borrowed time. Pulsars are the universe's ultimate timekeepers, spinning neutron stars that beam radiation across space with metronomic precision. But PSR J05406919 isn't just any pulsar. This rapid-fire remnant, nestled near the Tarantula Nebula, spins at a blistering 62 milliseconds per rotation, flashing like a cosmic strobe light. What makes it truly bizarre, though, is what's missing. Normally, pulsars sit at the heart of a supernova remnant, surrounded by the glowing wreckage of their parent star's explosion. Yet this one floats in eerie isolation, a celestial orphan with no visible debris field to call home. So where did its supernova go? One possibility is as dramatic as it is elusive. The explosion debris might be too faint to detect, scattered into an invisible haze by the pulsar's incredible speed. Neutron stars can be born with a violent kick, sometimes rocketing away at hundreds of miles per second. If PSR J05406919 got an especially powerful shove, it could have outpaced its own remnant, leaving the gas cloud too diffuse for telescopes to spot. Imagine a sprinter bolting from a smoke grenade. By the time the smoke disperses, the runner is long gone, leaving no trace of where they started. But there's another twist. This pulsar isn't just fast, it's also freakishly energetic. Its magnetic field crackles with intensity, driving powerful winds that push against any surrounding material. Over millennia, those particle streams could have carved out a cavity in the remnant, sweeping the gas aside like a cosmic plow. X-ray observations reveal faint hints of this interaction, a whisper-thin bubble of high-energy particles that might be all that remains of the original explosion's aftermath. The most tantalizing theory, though, involves a cosmic disappearing act. Some models suggest that under rare conditions, a supernova's shockwave can heat nearby gas so intensely that it becomes transparent, rendering the remnant effectively invisible to our telescopes. It's not that the debris isn't there, it's that we're looking right through it. If true, PSR J05406919's missing remnant could be hiding in plain sight, a ghostly shell waiting for the right instrument to reveal it. Whatever the explanation, this orphan pulsar challenges our understanding of stellar deaths. It's a reminder that even the most violent events in the universe can leave behind mysteries, and that sometimes what we can't see teaches us more than what we can. 35 years after its initial explosion, supernova 1987 is still putting on a show, but not in the way anyone expected. This stellar detonation, the closest observed supernova in modern history, should have faded into obscurity decades ago. Instead, something extraordinary is happening. Like a cosmic echo bouncing through caverns of dust, the light from that cataclysm is still reaching us, reflected and reshaped by vast interstellar clouds in the Large Magellanic Cloud. Hubble's time-lapse images capture this phenomenon in stunning detail. Luminous rings expanding outward like ripples from a stone tossed into a pond, each one a delayed snapshot of the original explosion's fury. These light echoes aren't just pretty afterimages, they're time machines. When the supernova first erupted, its flash illuminated pre-existing dust shells surrounding the doomed star. That light took years to reach the dust, bounce off, and finally travel to Earth, meaning we're seeing multiple replays of the same event from different angles and distances. The result, a three-dimensional dissection of the explosion's aftermath. The innermost rings, glowing blue in Hubble's ultraviolet filters, show the shockwave's earliest moments, while the outer, redder rings reveal how the blast interacted with colder, more distant material. It's as if the universe itself hit rewind, letting us study the supernova's anatomy frame by frame. But the echoes reveal something even more surprising. The dust isn't just scattering the light, it's transforming it. Spectroscopy shows the reflected light has subtly different wavelengths than the original blast, proof that these dust clouds are far from inert. Some grains are likely crystalline, their structures altered by the supernova's heat, while others contain complex molecules forged in the explosion's aftermath. This turns the echoes into cosmic alchemy labs, showing us how heavy elements from the dead star, carbon, oxygen, silicon, get incorporated into new generations of dust. The most haunting realization, this light show is temporary. As the echoes expand, they grow fainter, their energy dissipating into the void. Within centuries, they'll vanish entirely, leaving only the supernova's compact remnant, a neutron star or black hole, as silent testimony to the event. Yet for now, 1987 keeps speaking to us across the light years, its whispers carrying secrets about how stars die, how dust is born, and how even in destruction, the cosmos finds ways to echo its own history. Lurking in the Large Magellanic Cloud, two cosmic predators stalk the darkness, LMC X1 and X4, black holes locked in lethal embraces with their stellar companions. At first glance, they might seem like twins, both siphon gas from neighboring stars, Both blaze with X-rays as that material spirals inward. But peer closer, and their differences unveil a masterclass in how gravity warps reality. Take LMC X1 first. This black hole, 15 times the mass of our Sun, doesn't just feed, it feasts with grotesque elegance. Its accretion disk, that glowing whirlpool of doomed gas, isn't flat like a vinyl record. Instead, it's warped, twisted like a vinyl left too close to a flame. Why? The black hole's immense spin drags space-time itself into a vortex, bending the disk into a lopsided funnel. X-ray telescopes catch this distortion in action. One side of the disk glows hotter and brighter where gas piles up, compressed by the gravitational vice. It's as if the black hole prefers dining on one side of its plate, leaving the other oddly sparse. Now meet LMC X4, the cosmic strobe light. This system pairs a neutron star, an ultra-dense corpse no larger than a city, with a massive companion star, and together they stage one of the most baffling routines in the galaxy. Every 18 days, like clockwork, X4's X-ray emissions vanish. Not dim, not flicker. They shut off entirely for weeks before roaring back to life. The culprit, a mysterious warp in its accretion disk that periodically blocks our line of sight. Picture a spinning top wobbling so violently it occasionally tips sideways, eclipsing the neutron star's glare. But here's the puzzle. No known physics explains why the warp resets so precisely. Some theorists suspect hidden magnetic fields or tidal interactions with the companion star force this rhythm, turning X4 into a cosmic metronome. What's revelatory is how these systems mirror extremes. X1's warped disk showcases Einstein's theory in overdrive, a black hole so voracious it bends light and matter to its will. X4, by contrast, hints at forces we've yet to name, its rhythmic blackouts defying current models. Together, they prove that even in the violent dance of binary systems, no two steps are alike, and that the universe reserves its strangest choreography for those who watch closely enough to catch it. Globular clusters are usually the ancient guardians of a galaxy, dense, spherical collections of stars that formed billions of years ago, orbiting quietly in the outskirts like celestial museums. But NGC 1818 in the Large Magellanic Cloud is nothing like its cousins. For starters, it's shockingly young by globular standards, its brightest stars burning hot and blue instead of the cool red hues typical of old clusters. Even stranger, this cluster isn't just sitting still, it's moving like it's got somewhere else to be, streaking through the LMC with enough speed to suggest it might not belong here at all. So where did this rebellious cluster come from? Its trajectory and unusual composition point to a dramatic past. NGC 1818 stars share chemical fingerprints distinct from most LMC clusters, hinting they were forged in a different cosmic environment. The leading theory is as bold as the cluster itself. This might be an intergalactic thief snatched from another dwarf galaxy during a close encounter with the LMC. Picture two galaxies brushing past each other, gravity's invisible fingers plucking entire star clusters from one and depositing them into the other. If true, NGC 1818 is a cosmic transplant, its stars still carrying the chemical signature of their original home. But the youth of these stars adds another layer of intrigue. Most globular clusters are fossils from the early universe, but NGC 1818 stars are mere infants, some less than 100 million years old. That raises a tantalizing question. Did this cluster form in its original galaxy and then get captured, or was it born during the chaos of the galactic collision itself? Deep imaging reveals multiple generations of stars packed tightly together, suggesting it's been through multiple bursts of star formation, an anomaly for globulars which usually host stars all born around the same time. The most compelling clue lies in its orbit. Unlike most LMC clusters which circle the galaxy's core in neat, predictable paths, NGC 1818 barrels through at an odd angle, as if it hasn't yet settled into its new home. Some simulations suggest it might even be on a slow escape trajectory, destined to fling itself back into intergalactic space. Whether it stays or goes, one thing's certain: this cluster refuses to play by the rules, challenging our assumptions about how globulars form, move, and evolve. It's a cosmic drifter with a story still being written, and every observation peels back another layer of its mystery. Nestled within the chaos of the Tarantula Nebula, the Green Monster, nebula officially catalogued as N157b, glows with an otherworldly hue that seems ripped straight from a sci-fi fantasy. This isn't the gentle emerald of distant forests or the pale shimmer of auroras. It's a searing, almost electric green, a color so intense it cuts through the surrounding cosmic fog like a neon sign in the void. But this spectacle isn't just for show. Every photon of that eerie light tells a story of violence, speed, and forces so powerful they bend the rules of physics. The secret to the Green Monster's glow lies in its engine, a pulsar, the spinning corpse of a star that died in a supernova explosion. This particular pulsar, known as pulsar J0537-6910, whips around at a dizzying 62 milliseconds per rotation, its magnetic field accelerating particles to nearly the speed of light. As those particles slam into surrounding gas, they emit synchrotron radiation, a type of light produced when charged particles spiral violently around magnetic field lines. And here's the twist: synchrotron radiation favors specific wavelengths, and in N157b's case, that means an overwhelming surge of greenish light, amplified by oxygen emissions from the nebula's heated gas. But the color is only half the mystery. What makes this nebula truly bizarre is its structure. Most pulsar wind nebulae form neat, symmetrical bubbles or jagged tendrils, but the Green Monster is a tangled wreck. Hubble and Chandra images reveal a labyrinth of glowing filaments, some stretched into near-parallel lines, others twisted into knots as if some unseen hand crumpled them. The culprit: turbulence. The pulsar isn't just spewing particles, it's racing through space at over 1,000 kilometers per second. Its winds colliding with older supernova debris in chaotic shock fronts. Those collisions whip the magnetic fields into frenzied loops, which in turn sculpt the gas into these eerie, luminous ribbons. The most tantalizing detail, though, is what the Green Monster leaves behind. As the pulsar's particles plow through the nebula, they enrich it with heavy elements forged in the original supernova elements like neon, sulfur, and iron. Over time, these materials will disperse, seeding future generations of stars and planets. So while the nebula's green glow might steal the spotlight today, its real legacy is hidden in the chemistry of the cosmos, a fingerprint of stellar death that will linger long after the light fades. It's a reminder that even the universe's most dazzling spectacles are, at heart, silent alchemists transforming destruction into something new. Among the chaos of the Large Magellanic Cloud's outer edges, a cosmic ballet unfolds: the dancing ghost galaxy, officially known as SGS-3. This isn't your typical dwarf galaxy. It's a tattered, unraveling ribbon of stars caught in the act of being devoured by its larger neighbor. Deep field images reveal its haunting beauty, long, shimmering tidal tails stretching hundreds of light years like celestial streamers, marking the slow-motion destruction of an entire galactic system. What makes this spectacle so mesmerizing isn't just the sheer violence of the merger, it's how delicately the galaxy is being torn apart. Unlike dramatic collisions that ignite bursts of star formation, the dancing ghost is being disassembled almost gently, its stars peeled away one by the LMC's gravitational pull. The process is so gradual that the galaxy's core remains partially intact, a ghostly fingerprint of what it once was, while its outer layers smear across the cosmos like wet paint dragged across a canvas. Hubble's sharp gaze catches the intricate details of this disintegration. The tidal tails aren't just featureless streaks. They're studded with star clusters and glowing knots of gas, each a testament to the dwarf galaxy's former structure. Some of these clusters are so densely packed they resemble miniature galaxies themselves, stubbornly holding together even as the wider system dissolves. Meanwhile, the galaxy's core, what's left of it, flickers with the faint light of aging stars, their orbits thrown into chaos by the relentless tug of the LMC's gravity. But the real mystery lies in the debris trails. These tidal tails curve in unexpected ways, their shapes hinting at invisible forces at work. Computer simulations suggest the LMC's dark matter halo, an unseen gravitational scaffold, is warping the dwarf's remains, sculpting the streams into these graceful, looping arcs. It's as if the galaxy isn't just falling apart. It's being choreographed, its final dance directed by the hidden hand of dark matter, the most haunting realization. This isn't a rare event. The dancing ghost is just one of many small galaxies being absorbed by the LMC, a process that's been playing out for billions of years. Each merger leaves behind traces, filaments of stars, rogue clusters, even orphan black holes slowly blending into the larger galaxy's fabric. In that sense, the dancing ghost isn't just a victim of cosmic forces, it's a contributor. It's stars and gas destined to become part of the LMC's future. And as we watch its final act, we're reminded that even in destruction, there's renewal, the universe's endless cycle of endings and beginnings written in starlight. Deep within the Large Magellanic Cloud, two nebulae defy the chaotic sprawl of their surroundings with structures so precise they seem sculpted by an invisible hand. N159, nicknamed the Papillon Nebula for its stunning butterfly-like symmetry, stretches its luminous wings across 150 light-years of space. But this isn't just a cosmic Rorschach test. Every curve and filament tells a story of extreme physics. At its heart lies a runaway star, barreling through the gas at breakneck speed and carving out the nebula's delicate shape with its stellar winds. JWST infrared eyes reveal the hidden mechanics. Searing ultraviolet radiation from the central star heats the surrounding hydrogen, causing it to fluoresce pink in visible light while dust layers glow orange in infrared, creating a celestial stained glass window. What makes the Papillon truly remarkable isn't just its beauty, it's the violence required to maintain such perfect form. Most nebulae churn with turbulence, their edges frayed by external forces. But here, the star's motion and radiation balance perfectly against the pressure of the surrounding molecular cloud, creating a rare equilibrium where structure persists against the chaos. The butterfly's wings are actually bubbles expanding cavities blown by the star's winds, their rims compressed into sharp ridges where new stars are beginning to ignite. It's a self-perpetuating cycle. The same forces that sculpt the nebula also trigger fresh rounds of star formation along its edges, ensuring the cosmic artwork won't fade without leaving a legacy. Just a cosmic stone's throw away, N160 presents a stark contrast. Where the Papillon is all elegance, this nebula is a factory floor, a gritty, bustling stellar nursery where towering pillars of dust rise like skyscrapers against a backdrop of glowing gas. JWST infrared piercing gaze exposes details invisible to optical telescopes. Newborn stars still swaddled in their dusty cocoons, their faint heat signatures betraying their presence as they greedily accrete material. These pillars, reminiscent of the famous pillars of creation in our own galaxy, are under constant assault. Radiation from nearby massive stars erodes their surfaces, sending streams of evaporating gas into space, a process called photoevaporation that simultaneously destroys the pillars while exposing the infant stars within. The most startling revelation from JWST lies in N160's chemistry. Spectral analysis shows these pillars are laced with complex organic molecules, including polycyclic aromatic hydrocarbons, carbon-based compounds essential for life. They shouldn't survive this close to such intense radiation, yet here they thrive, perhaps shielded within the densest knots of gas. It's a tantalizing hint that even in these hostile environments, the building blocks of life can persist, waiting to be incorporated into future planetary systems. Together, N159 and N160 showcase the duality of creation. One a masterpiece of balance, the other a testament to the raw, unbridled forces that shape galaxies. And through JWST lens, we're witnessing their stories unfold in unprecedented detail, one infrared photon at a time. VFTS 243 is the cosmic equivalent of a detective novel where the killer vanishes without a trace. Only in this case, it's not a criminal that's missing, but an entire black hole. On the surface, this binary system in the Large Magellanic Cloud looks ordinary. A massive blue supergiant star 25 times heavier than our Sun, drifting peacefully through space. But something's off. The star isn't dancing with another luminous companion, it's orbiting empty space, locked in a gravitational tango with something completely invisible. Measurements don't lie. The star's motion betrays an unseen partner weighing at least 9 solar masses, tugging it along an elliptical path. Normally, an object that massive would be blatantly obvious, a pulsar flashing like a lighthouse, or a black hole ripping gas from its neighbor and lighting up the cosmos with X-rays. Yet here, there's no accretion disk, no stellar winds being stolen, no telltale glow of doomed matter heating up as it spirals into oblivion, just silence. So what kind of black hole hides this well? Astronomers are staring at what might be the first confirmed example of a quiet black hole, one that formed without the fanfare of a supernova. The leading theory is as unsettling as it is elegant. Most black holes are born in violent explosions, their progenitor stars blasting away their outer layers in spectacular supernova before their cores collapse. But VFTS 243's invisible companion might have skipped the fireworks entirely. Instead of exploding, its star could have imploded directly into a black hole, like a building collapsing inward so cleanly that not even a dust cloud rises from the wreckage. Simulations support this idea. Under very specific conditions, low metal content, rapid rotation, a massive star's core might collapse so efficiently that the outer layers slump inward too, leaving no material to ignite a supernova. The result, a black hole forms without a sound, slipping into the cosmic shadows undetected. The only clue it leaves behind is the wobble of its bewildered stellar partner, still circling the void where its twin used to be. But here's the twist. If this theory holds, VFTS 243 isn't just an oddity, it's a paradigm shift. For decades, astronomers assumed black holes always announced their births with supernova. This system suggests there might be an entire population of black holes lurking unseen, their formation so quiet we've missed them entirely. It's a humbling thought. Even in a galaxy as thoroughly studied as the Large Magellanic Cloud, the universe is still teaching us how little we truly know about stellar life and death. Winding through the outskirts of the Large Magellanic Cloud like a cosmic scar, the LMC4 stellar stream tells a violent story written in starlight. This faint ribbon of ancient suns, barely visible against the galaxy's glow, isn't just another cluster, it's forensic evidence of a catastrophic collision that reshaped the LMC billions of years ago. Unlike the galaxy's bustling star-forming regions, this stream is eerily quiet, its stars old and metal poor, relics from a time when the LMC was still assembling itself through brute force. Tracing the stream's arc reveals its origins. These stars move in lockstep along a precise curve, their motion betraying the gravitational hand that flung them here. Computer simulations reconstruct the scene, a smaller dwarf galaxy, perhaps 1/10 the LMC's mass, careening too close in the distant past. The tidal forces would have been apocalyptic. Imagine a hammer swinging through a cloud of glitter, scattering stars in long, looping trails. Over eons, the victim galaxy dissolved entirely, leaving only this glittering smear as its tombstone. What makes LMC4 extraordinary isn't just its existence, it's how perfectly preserved it remains. Most stellar streams fray over time, their stars gradually mixing into the galactic halo. But LMC4's coherence suggests the LMC's dark matter halo. Its invisible gravitational scaffold acted like a cosmic spiderweb, catching and suspending the stream in near-perfect formation. Gaia spacecraft data confirms this. The stars share nearly identical velocities, as if frozen in the moment of their ejection. The real revelation lies in the stream's chemistry. Spectroscopy shows these stars contain barely any heavy elements, proof they formed early in the universe's history, before supernova had seeded space with metals. That makes LMC4 a living time capsule, offering a glimpse into the LMC's youth. Even more intriguing, the stream's path suggests the collision didn't just scatter stars, it triggered cascading waves of star formation elsewhere in the LMC, like ripples from a stone tossed into a pond. Today, the stream serves as a celestial blueprint, helping astronomers reconstruct not just this single collision, but the entire merger history of the LMC. Similar structures likely exist, still hidden in the galaxy's outskirts, ghostly signatures of other long-vanished galaxies sacrificed to build the cosmic island we see today. In that sense, LMC4 isn't just a fossil. It's the first chapter in a biography of violence written in stars too old to forget. Stretching across 150 light-years of space, the supernova remnant SNR 0509-67.5 doesn't just mark the death of a star, it weaves a celestial tapestry so intricate it could pass for an interstellar spiderweb. Hubble's razor-sharp vision reveals filaments of glowing gas crisscrossing in a delicate lattice, each thread a luminous scar from the explosion that tore this star apart 400 years ago. But this isn't random debris. The remnant structure is eerily symmetrical, its filaments radiating outward like spokes on a wheel, frozen in the moment of their violent birth. What makes this cosmic web so mesmerizing isn't just its beauty, it's the physics encoded in every strand. Each filament glows in specific wavelengths, revealing its chemical composition. Oxygen burns blue where shockwaves heat it to millions of degrees, while cooler sulfur and hydrogen paint the structure in reds and greens. Together, they form a three-dimensional map of the star's final moments, showing how the explosion rippled through surrounding space. The filaments aren't static either. Time-lapse observations catch them slowly expanding, their delicate dance unfolding over decades as they encounter pockets of interstellar gas that bend and twist their paths. The real mystery lies in how such fragile-looking structures endure. Supernova unleash enough energy to vaporize nearby dust clouds, yet these filaments persist, their threads remaining coherent across vast distances. The secret magnetic fields, like invisible wires, they channel and stabilize the expanding gas, preventing it from dissipating into chaos. Hubble's polarized light measurements reveal these fields threading through the remnant, their lines tracing the same patterns as the glowing filaments, proof that magnetism is the unseen hand sculpting this cosmic artwork. But SNR 0509's story doesn't end with its filaments. At its heart lies another enigma, the ghost of the star that created it. Most supernova leave behind a neutron star or black hole, yet deep searches reveal nothing. No pulsar, no X-ray source, just silence. Some astronomers speculate the collapse was so complete that even the core vanished without a trace. Others propose an exotic scenario where the star's explosion flung its remnant clear of the debris at incredible speed, leaving behind a runaway corpse streaking unseen through the galaxy. Whether the remnant's heart is missing or hiding, one thing's certain: this supernova spun destruction into something strangely elegant. Its filaments aren't just wreckage, they're a testament to how chaos, guided by invisible forces, can create order on a cosmic scale. And as Hubble continues to watch, each new image adds another thread to the story, weaving together the science and the spectacle of stellar death. The star SK -69°202 was supposed to die. 35 years ago, astronomers watched with anticipation as its violent demise lit up the night sky. Supernova 1987A, the closest stellar explosion witnessed in modern history. Conventional wisdom said the star should have been obliterated, its core collapsing into a neutron star or black hole while its outer layers were blasted into space. But the universe loves a good plot twist. Recent observations suggest SK negative 69 degrees 202 might not be gone at all. Somewhere in that swirling debris field, a fragment of the original star could still be clinging to existence, a cosmic zombie that somehow survived its own destruction. The evidence comes from an unexpected glow. When Hubble turned its eye toward the supernova remnant, it detected a persistent source of ultraviolet light right where the star's core should have been. This isn't the steady pulse of a neutron star or the telltale X-ray signature of an accreting black hole. It's a fainter, cooler emission, as if a shard of the original star is still burning. One theory suggests the supernova wasn't powerful enough to completely disrupt SK negative 69 degrees 202. Instead of a full collapse, the star's core might have rebounded at the last moment, leaving behind a mangled stellar remnant, a white dwarf or highly distorted neutron star still hot enough to emit ultraviolet light but too damaged to behave like a typical compact object. Another possibility is even stranger. Some models propose the star didn't explode outward at all, it imploded inward, triggering a runaway fusion reaction deep in its core that temporarily reignited its nuclear furnace. In this scenario, what we witnessed in 1987 wasn't a true supernova but a failed one, a botched explosion that left the star wounded but alive. The ultraviolet glow could then be the star's last gasp, radiating energy as it slowly cools from the traumatic event. The most tantalizing clue, the remnant's chemical fingerprints. Spectroscopy shows an overabundance of helium and hydrogen in the debris, elements that should have been consumed or expelled during a standard supernova. Their persistence hints that parts of the star's outer layers fell back onto the core after the explosion, like material collapsing onto a trampoline instead of being flung into space. If confirmed, SK negative 69 degrees 202 would be the first known example of a supernova survivor, a star that flirted with annihilation and lived to tell the tale. This cosmic defiance forces astronomers to rethink what they know about stellar deaths. For decades, textbooks painted supernova as definitive endpoints. Now, the zombie star suggests some stellar explosions might be more like violent transformations, events that reshape stars without completely destroying them. And if one star can cheat death, how many others in the universe might be hiding in plain sight, masquerading as supernova remnants while quietly burning in the shadows? The answer could rewrite our understanding of how stars live, die, and sometimes refuse to go gently into that good night. In the heart of NGC 2173, a globular cluster older than our solar system, something impossible gleams against the dark, stars that shouldn't shine blue. These ancient suns, dubbed blue hook stars, burn with the searing hue of stellar youth despite being nearly twice as old as Earth. Their color defies everything we know about stellar evolution. Normally, aging stars redden as they exhaust their hydrogen fuel and expand into cool giants. But here, in this crowded corner of the Large Magellanic Cloud, nature rewrites the rules with a cosmic sleight of hand. The secret lies in delayed helium fusion, a stellar midlife crisis playing out on a galactic scale. Most stars begin fusing helium in their cores predictably, but blue hook stars resist this transition with bizarre stubbornness. Their cores grow denser and hotter than usual, postponing the ignition of helium in a way that mimics the energy output of much younger stars. This extended hydrogen burning phase supercharges their outer layers, making them appear paradoxically blue despite their advanced age. It's as if these stars discovered a cosmic fountain of youth, burning brighter and bluer just when they should be fading into red obscurity, But there's another twist to this tale: stellar collisions. In the crowded core of NGC 2173, stars brush past each other like dancers in a packed ballroom. Occasionally, two aging stars lock in a gravitational embrace, merging into a single, rejuvenated object. These violent unions stir up fresh hydrogen from deep within the star's interiors, dumping new fuel onto their cores and effectively resetting their evolutionary clocks. The resulting hybrid star burns hotter and bluer than either of its predecessors, mimicking a youthful appearance while hiding centuries of cosmic history beneath its surface. Hubble's ultraviolet observations reveal the fingerprints of this drama. Blue hook stars show unusual chemical abundances, extra carbon and oxygen in their atmospheres, the telltale remnants of internal mixing triggered by delayed helium fusion or merger-driven turbulence. Some even sport enhanced helium levels, evidence of deep material being dredged up from their cores. These anomalies confirm that blue hook stars aren't just oddities. They're cosmic chameleons rewriting their own life stories through physics we're only beginning to understand. What's most remarkable is how these stars challenge our assumptions. For decades, astronomers used color as a reliable indicator of a star's age and mass. But the blue hook phenomenon proves that stellar evolution isn't always a one-way street. Sometimes, through sheer chance or cosmic collisions, stars find ways to turn back the clock. And in doing so, they remind us that even the most well-studied corners of the universe still hold surprises, waiting to upend our expectations, one glittering mystery at a time. The Large Magellanic Cloud spins like a cosmic top, but not evenly. Unlike the Milky Way's graceful, balanced rotation, the LMC's outer regions whip around faster than they should, as if gripped by an invisible hand. This mismatch between visible mass and motion is one of the strongest hints that dark matter, the universe's most elusive substance, is woven into the galaxy's very fabric. Imagine a carousel where the outer horses inexplicably outpace the inner ones despite no apparent force pushing them. That's the enigma astronomers face when mapping the LMC's spin. Observing this anomaly requires precision. By tracking the movements of hydrogen clouds and young stars across the galaxy, researchers reconstruct its rotation curve, a graph showing how orbital speeds change with distance from the center. In a typical system like the Milky Way, speeds peak near the middle, then gradually decline as gravity weakens farther out. But the LMC's curve stays suspiciously flat, its outer regions maintaining nearly the same velocity as the inner ones. The only explanation: additional mass. Lots of it must be lurking unseen, its gravity propping up those distant stars and gas clouds like an invisible scaffold. Here's where dark matter's fingerprints emerge. Current models suggest the LMC's visible stars and gas account for barely 1/10 the gravity needed to explain its rotation. The rest likely comes from a vast halo of dark matter enveloping the galaxy, extending far beyond its luminous edges. Unlike the Milky Way's more symmetrical dark matter distribution, the LMC's halo appears lopsided, possibly warped by past encounters with the small Magellanic Cloud or our own galaxy. Computer simulations show such interactions could stretch the halo into an elongated shape, its uneven pull distorting the rotation curve in exactly the ways we observe. The implications ripple beyond this single galaxy. Comparing the LMC's spin to the Milky Way's reveals a startling pattern. Dwarf galaxies consistently rotate faster than standard physics predicts for their visible mass. This discrepancy first hinted at dark matter's existence decades ago, but the LMC, so close we can study it in granular detail, offers a rare chance to test the theory. If dark matter truly molds its rotation, the LMC could become a Rosetta Stone for understanding how this mysterious substance shapes galaxies of all sizes. Yet mysteries linger. Some alternative theories propose modified gravity laws instead of dark matter, though none yet fully explain the LMC's quirks without invoking unseen mass. What's clear is that this uneven spin isn't just a curiosity, it's a cosmic breadcrumb trail. By decoding the LMC's motion, we're not just studying one galaxy's behavior, we're peering into the hidden architecture of the universe itself. And every new measurement brings us closer to answering the ultimate question: what really holds the cosmos together? The Henais 206 Nebula isn't just another star factory. It's a cosmic pressure cooker where gas doesn't simply collapse into stars but writhes in violent, chaotic knots. Unlike the serene glow of many nebulae, this region of the Large Magellanic Cloud churns with turbulence so extreme it defies conventional models of star formation. Hubble's snapshots reveal a landscape of walls and eddies, as if the nebula's gas has been stirred by a gargantuan, invisible spoon. But what's fueling this frenzy? The answer lies in a cycle of destruction and rebirth that's been playing out for millions of years. At the heart of Henais 206's chaos are the ghosts of dead stars' supernova remnants whose shockwaves continue to reverberate through the nebula long after the explosions faded. When a massive star dies, it doesn't just vanish. It unleashes a tsunami of energy that slams into nearby gas clouds, compressing them into dense, jagged filaments. These shockwaves don't just reshape the nebula, they supercharge it. Telescopes like Spitzer and Chandra spot the aftermath, pockets of gas heated to searing temperatures, their atoms ionized by the relentless pounding of these cosmic tsunamis. And where the waves collide, something extraordinary happens. The compressed gas reaches critical density, collapsing under its own gravity to ignite new stars. It's a stellar domino effect, one generation's death giving rise to the next. But here's the twist: Henais 206's turbulence isn't just a side effect of supernova, it's a self-perpetuating engine. The newborn stars, themselves massive and volatile, soon unleash their own fury. Their stellar winds, blasting outward at millions of miles per hour, carve cavities in the surrounding gas, creating fresh shock fronts that collide with older ones. The result is a feedback loop of violence, where each wave of star birth sows the seeds for the next round of destruction and renewal. Alma radio eyes peer deep into this maelstrom, revealing intricate networks of gas threads twisted into braids and knots by these competing forces, a roadmap of the nebula's turbulent history written in molecular dust. What makes Henais 206 truly remarkable is how it mirrors the conditions of the early universe. In an era before galaxies settled into orderly spirals, star formation was a messy, brutal affair driven by constant upheaval. This nebula offers a rare nearby laboratory to study those primal processes. Its chaos isn't random, it's a finely tuned mechanism where turbulence doesn't hinder star birth but accelerates it, shredding gas clouds into fragments just the right size to collapse into stars. And so, the cycle continues: supernova blast, gas churns, stars ignite, and the nebula's fury fuels its own future. It's a reminder that in the cosmos, even disorder has a purpose. The same forces that tear things apart are the ones that build them anew. Tucked away in the Large Magellanic Cloud's outer halo, globular cluster NGC 2210 gleams like a cosmic relic, a time capsule preserving stellar secrets from over 11 billion years ago. But what makes this ancient cluster truly remarkable isn't just its age. It's how strikingly similar its chemical makeup is to our Milky Way's own globulars, despite forming in an entirely different galaxy. Imagine finding a book written in the same language but on another continent, untouched by the local culture. That's the Enigma NGC 2210 presents, a celestial paradox that forces us to rethink how galaxies evolve independently while still following universal rules of star formation. Deep spectroscopic analysis reveals the cluster's stars contain nearly identical ratios of heavy elements, what astronomers call metallicity, as their Milky Way counterparts from the same cosmic era. This shouldn't be possible if the LMC evolved in isolation, since each galaxy's star-forming history leaves distinct chemical fingerprints. one would expect differences in oxygen, sodium, or iron levels based on varying supernova rates or gas inflow patterns. Yet NGC 2210's composition aligns almost perfectly with ancient Milky Way clusters like M92, hinting at a shared universal recipe for early star formation that transcended galactic boundaries. The implications ripple outward. This chemical mirroring suggests the LMC's earliest star-forming environment, its primordial gas clouds and supernova yields, must have operated under nearly identical conditions to the Milky Way's, despite the two galaxies evolving separately for billions of years. It's as if the universe had a strict template for how the first stellar generations should form, one that overpowered local galactic quirks, yet NGC 2210 isn't a perfect copy. Subtle deviations lurk in the date, a slight overabundance of carbon here, a deficit of magnesium there. These tiny anomalies are the real treasure, the fingerprints of the LMC's unique evolution. Unlike the Milky Way, which grew through violent mergers that repeatedly stirred its chemical pot, the LMC's relative isolation allowed some primordial signatures to persist untouched. The cluster's outliers may trace back to the dwarf galaxy's quieter history, where fewer collisions meant less contamination from external gas streams or disrupted star clusters. Hubble's sharp gaze captures another clue, the cluster's spatial distribution. While Milky Way globulars often orbit in neat, spherical halos, NGC 2210 drifts along an elongated path in the LMC's outskirts. This suggests it might have formed during the galaxy's chaotic infancy, when gravitational instabilities flung early clusters into eccentric orbits. The same processes likely shaped its chemical peculiarities, as its stars condensed from gas clouds that experienced slightly different enrichment histories than those in our galaxy. The ultimate mystery, why this cluster, and only a handful of others in the LMC, retained such strong Milky Way-like traits while most LMC globulars diverged chemically over time. Some theorists propose NGC 2210 formed during a rare epoch of stability, when the LMC's gas reservoir was unusually well mixed. Others speculate it might be a captured object, stolen from another dwarf galaxy that coincidentally mirrored the Milky Way's early chemistry. Whatever the explanation, NGC 2210 stands as a testament to both cosmic uniformity and galactic individuality, a reminder that the universe follows grand patterns yet leaves room for local flair. Its ancient starlight carries dual messages, that some rules of star formation are universal, but no two galaxies ever tell exactly the same story. The Tarantula Nebula dazzles with its stellar fireworks, but beneath the brilliant glow lies a graveyard of cosmic mysteries where the expected remains of dead stars are conspicuously absent. Supernova should pepper this region with remnants, glowing debris fields, and spinning neutron stars marking the explosive deaths of massive suns. Yet when astronomers tally the numbers, something doesn't add up. Given the nebula's frenetic star formation, theorists predict at least 30 supernova remnants should dot its expanse. But fewer than half that number have been found, their ghostly outlines eluding even the most advanced telescopes. Where did all the dead stars go? One possibility is as unsettling as it is plausible: black holes, and not the ordinary kind. The tarantula's intense environment might birth black holes so massive they swallow their own supernova whole. Imagine a star so colossal that when its core collapses, not even a shockwave escapes. Instead of erupting outward, the entire implosion vanishes behind an event horizon, leaving no trace beyond a gravitational whisper. These failed supernova could explain the missing remnants, their absence a silent testament to stars dying not with a bang, but a whimper. Supporting this theory are erratic stars in the region that appear to orbit invisible partners, dark companions weighing dozens of times our sun's mass, far too heavy for neutron stars. Could these be the tarantula's hidden black holes, lurking unseen after their violent births? Yet even this explanation doesn't account for the nebula's most bizarre vanishing act. Take the case of Sanjalik minus 69 degrees 202, the progenitor of supernova 1987A. Its explosion left behind a neutron star, except no one can find it. Decades of searching with radio, X-ray, and infrared telescopes have turned up nothing but an eerie quiet where a pulsar's pulse should be. Some speculate the remnant might be shrouded in ultra-dense dust, while others propose it was launched into deep space at incredible speed, a cosmic bullet escaping its own crime scene. The tarantula's future only deepens the intrigue. Within a few million years, a blink in cosmic time, its current crop of massive stars will exhaust their fuel, triggering a cascade of supernova that could dwarf anything we've witnessed. Simulations suggest these explosions might merge into a collective shockwave, powerful enough to blow the nebula apart from within. Gas and dust would scatter into intergalactic space, leaving behind a glittering skeleton of surviving stars and compact remnants. But here's the twist: the same forces that destroy the tarantula could also seed new beginnings. Shockwaves from the detonations will plow into surrounding gas clouds, compressing them into fresh stellar nurseries. The nebula's death throes might ignite the next generation of stars, ensuring its legacy endures long after its iconic glow fades. Perhaps the ultimate mystery isn't what's missing, but what's yet to come. The Tarantula Nebula is a living laboratory, its secrets evolving faster than we can unravel them. Every unanswered question, the vanished remnants, the rogue black holes, its impending transformation serves as a reminder that even the brightest corners of the cosmos hold shadows we're only beginning to explore. Peering into the Large Magellanic Cloud demands more than just powerful telescopes. It requires an arsenal of specialized instruments, each designed to capture different pieces of the cosmic puzzle. Take Hubble, for instance, with its razor-sharp vision spanning ultraviolet to near-infrared. This iconic telescope has mapped the LMC's stellar nurseries in breathtaking detail, revealing the delicate filaments of the Tarantula Nebula and the ghostly glow of ancient star clusters. But Hubble's true genius lies in its ability to freeze time. By comparing images taken decades apart, astronomers have tracked the slow expansion of supernova remnants like SNR 0509, measuring shockwaves that crawl across space at thousands of miles per second, motions so gradual they'd be invisible without Hubble's patient gaze. Then there's JWST, Hubble's infrared successor, which peers through the LMC's dust veils like an X-ray machine scanning cosmic bones. Where Hubble sees obscuring clouds, JWST spots the heat signatures of newborn stars still cocooned in their dusty wombs. Its spectrographs dissect the chemical fingerprints of nebulae, uncovering complex organic molecules lurking in regions like N160 molecules that shouldn't survive such hostile radiation but thrive nonetheless. JWST's greatest triumph in the LMC, capturing the faint infrared whispers of the universe's first galaxies lurking behind the dwarf galaxy, using its gravitational mass as a natural lens to magnify light from the cosmic dawn. But to understand the LMC's hidden dynamics, astronomers turn to ALMA, a network of radio dishes perched high in Chile's Atacama Desert. While optical telescopes show where stars are, ALMA reveals where they'll be, mapping the frigid molecular clouds where future stars gestate. Its millimeter-wave vision spots carbon monoxide and other molecules freezing onto dust grains, the primordial ingredients of planets. ALMA's finest hour came when it traced the LMC's chaotic magnetic fields, detecting how they twist around supernova shocks like invisible threads guiding the galaxy's evolution. Studying the LMC isn't without quirks. Unlike distant galaxies whose light reddens dramatically as space stretches during its long journey to Earth, the LMC's proximity means its redshift is barely detectable. This nearness eliminates a key tool astronomers use to measure cosmic distances and velocities. Instead, researchers rely on subtle stellar pulsations and the motions of gas clouds tracked over years, painstaking work that turns the LMC into both a laboratory and a benchmark, helping calibrate methods used across the universe. The real magic happens when these telescopes collaborate. Hubble pinpoints a supernova remnant, JWST analyzes its chemistry, and ALMA tracks how its shockwaves reshape nearby gas. Together, they transform the LMC from a smudge of light into a living, breathing entity, a cosmic workshop where the laws of physics are both obeyed and rewritten. And with each new observation, this humble dwarf galaxy reminds us that the universe's grandest secrets often hide in plain sight, waiting for the right tools to reveal them. From runaway stars to phantom black holes, the Large Magellanic Cloud isn't just a neighboring galaxy, it's a cosmic playground where the universe tests its most extreme physics. These 30 phenomena represent more than celestial oddities. They're a masterclass in how stars live, die, and defy expectations. The LMC's turbulent star factories, ghostly remnants, and gravitational illusions offer something rare, a front-row seat to processes that shaped the early universe, unfolding right in our cosmic backyard. Whether it's the Tarantula Nebula's violent stellar nurseries or the eerie silence of vanished supernova, each mystery peels back another layer of astrophysical truth, proving that sometimes the smallest galaxies hold the biggest revelations. For those under southern skies, the LMC is more than a smudge of light, it's a living map of these wonders. On clear nights away from city lights, its hazy glow near the constellation Dorado reveals the tapestry we've explored, the faint shimmer of the Tarantula Nebula, the subtle contrast of the dark river's dust lanes, even the unseen pull of dark matter warping the galaxy's spin. Grab binoculars or a small telescope, and you're not just stargazing, you're witnessing cosmic history in real time, where distant supernova echoes and hypervelocity stars write their stories across the void. But the greatest lesson the LMC teaches isn't about specific phenomena, it's about perspective. This dwarf galaxy reminds us that the universe thrives on chaos and contradiction, where stars cheat death, black holes hide in plain sight, and even dust holds the blueprint for new worlds. Every observation, every unanswered question invites us to look deeper and stay curious. So whether your team R136 is stellar monsters or fascinated by the dancing ghosts' tidal tales, drop a comment below. Which of these cosmic marvels left you awestruck? The conversation doesn't end here. It's just another spark in the LMC's endless fireworks show of discovery.